going.
Bubble, say hello.
Bubble says hi.
This is Bubble. Bubble is Queen Bubble, or Princess Bubble. Bubble doesn't have all of her legs. As you can see, Bubble is very special and a little fussy. Bubble's going to be leaving very soon, but Bubble wanted to say hi to Honors Chemistry. So this is Bubble. Now we're gonna take her away and put her by Sherry, where she can fight. And we're going to discuss Lewis dot structures for elements. If you're talking about bonding, you need a way to represent electrons. If you guys remember, hydrogen has an electron configuration of 1s1, and hydrogen has 1 dot. Lewis dot structures or electron dot structures use a dot to represent electrons. In helium, we have a configuration of 1s2. It means there are 2 valence electrons or outer shell electrons. And the Lewis dot structure for helium looks like that. The whole idea with Lewis dot structures is that you want to form a square around the element with your electrons. There it is. There's the pen. So, for instance, if I have element X, this is not the good pen, element X, I want to get the electrons in the Lewis dot structure around it like this. And I'm going to put them top to top, side to side, then one or the other, and then gradually fill them up. So that's what I'm trying to do here. So hydrogen has 1. I could have put this electron for hydrogen on the top or either side. Don't worry about writing this down. I'm going to put a copy of this in Google Classroom, but I want to talk about how we got to it before you just see this piece of paper. Okay, so helium has a configuration of 1s2, 2 valence electrons right here. Those are the 2 valence electrons, 2 dots. Lithium, 1s2, 2s1. I've underlined its single valence electron, and so we've got 1 dot. You go to beryllium, it has 4 electrons, a configuration of 1s2, 2s2. The valence electrons are in the 2s shell, subshell, and they're here and here. If you go to boron, you've got 1s2, and then these remaining 3 electrons in the 2s and the 2p orbitals are the valence electrons. So boron has 3 dots. Notice I haven't paired any of these dots up yet. Carbon with 6 electrons is a configuration of 1s2, 2s2, 2p2. These are the valence electrons. The highest n quantum number gives you the valence electrons. So 2 plus 2 is 4, so carbon goes 1, 2, 3, 4. After you have 4 electrons around the symbol for the element, you can start pairing them up. Nitrogen has 5 valence electrons. Here's its configuration, 1s2, 2s2, 2p3, 2 plus 3 is 5. So we've gone 1, 2, 3, 4, 5. With oxygen's 6 valence electrons, okay, its whole configuration, 1s2, 2s2, 2p4. These guys, the 2 and the 4, are valence electrons. Oxygen goes 1, 2, 3, 4, and then 5 and 6. I could have put the pairs above. I could have put them next to each other. I tend to just like them to be symmetric. Fluorine has 9 electrons, and it has 7 valence electrons, 1s2, 2s2, 2p5. The underlined electrons are the valence electrons, and we're going to have 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. When we get to neon, you've got 8 electrons in the valence shell, 10 electrons altogether, and each of those sides is paired up. 1, 2, 3, 4, 5, 6, 7, 8. Then it repeats with sodium. It's just a little bit bigger, 3s1, if you compare it to lithium, which is 2s1. But we go back to 1 valence electron. Group 2 has 2 valence electrons. Zip over to group 13, we have 3 valence electrons, the 3s2 and the 3p1, going all the way to the edge of the 3rd period with argon, which has a complete completely filled s orbital and a completely filled p subshell, 2 plus 6 is going to give you 8 valence electrons, and argon has 8. So I'm going to post this in Google Classroom, as I said, but when you look at it, don't flip out. What you want to pay attention to is the underlying valence electrons, how many there are, and where they are with respect to the elemental symbol.